This problem has a few pieces we can assemble before solving it. First, let's find the direction and magnitude of the electric field between the plates. The bottom plate is positive, so the electric field is directed from it to the top plate. We know the electric field between the plates is constant. It's the battery voltage divided by the plate spacing. That gives us its magnitude of 1.83 times 10 to the fourth volts per meter. Now let's find the alpha particle speed as it enters the region between these two plates. We're told the alpha particle starts from rest and accelerates through a potential difference of 1.75 kilovolts. Because the particle's kinetic energy increases, conservation of energy tells us that its potential energy must decrease. The charge is positive, so this potential difference must be negative. If we then write a statement of energy conservation, there is no work being done by forces other than the electric force. We can express the change in kinetic energy as 1/2 m times the final speed squared, and the change in potential energy is the charge times the change in electric potential. That charge is twice the fundamental charge, so we can solve for the alpha particle's final speed. It's given by this expression, and we can substitute all the values. 4 times the fundamental charge times the potential difference divided by the alpha particle's mass. Watching all the negative signs, we find the alpha particle enters the region between the two plates with this final speed. Now we can solve the problem using the fact that the particle travels undeflected through those two plates. That means the force on it, which is the Lorentz force I'll write here, equals 0. If the force equals 0, this term in parentheses must equal 0, which tells us that the electric field equals minus V cross B. They're in opposite directions with the same magnitude. The electric field is directed up, so the V cross B term must be directed down. Using the right-hand rule, with the velocity going to the right, we see this means the magnetic field, that I'll draw in green, must be directed out of the screen. So now we know the direction of the magnetic field, and we just need its magnitude. We can solve for that by coming back to the equation E equals minus V cross B. These three vectors are mutually perpendicular, so we can solve for the magnitude of B, setting it equal to the magnitude of the electric field divided by the speed. Substitute the numbers we calculated before to find that the magnetic field has a magnitude of 4.45 times 10 to the minus 2 Tesla, and is directed out of the screen.